Okay, in this question, we are calculating pH. Now we can think of this much like a titration. We've added to a weak base a strong acid. Now it doesn't say titrate, but essentially it is the same. Now, we don't know specifically if this is at the halfway point or the equivalence point, or we've exceeded the amount of moles of weak base. And so we're in a place where we're calculating just the H plus from the excess acid. So the first thing we need to do is figure out how many moles of strong acid and how many moles of weak base have been added. They're both 1-to-1. So let's take a look. So HBr, we have 0.200 moles per liter times 0.060 liters. So that would be 0.012. Now for our weak base, we have 0.400 moles per liter, and it's times 0.3. Now I see one is double, one is half, so that's going to be the same amount of moles of okay, so what we have here is an equivalence point. We're at the equivalence point. And so what happens there is that we've eliminated all of the weak base and created its conjugate acid, right? So CH3 NH2 plus HBr, creating H, CH3 NH2. So we've created this. Now this is in one direction, right? This is not equilibrium. So we've created this conjugate acid of the weak base. And now in solution, this is like how when we first learn acids and bases, so we have a weak base in there and we learned how to calculate pH. This weak base is in an equilibrium state. Equilibrium means the reaction is continually happening, right? It's not just going to completion and finishing. So we're at an equilibrium where we're creating this weak base and H3O plus. So this equilibrium is happening. So it's the forward rate is equal to the reverse rate. This is happening at the equivalence point. And so it's creating an acid. And so like we would expect, right? We learned that if you are titrating a weak base with a strong acid, the pH of the equivalence point should be under 7. If you're titrating a weak acid with a strong base, the equivalence point should be at above 7 because you've created a conjugate base. In this one, we've created a conjugate acid, which while it's sitting in solution, is creating these H3O pluses. So we are going to first figure out what is our concentration of this conjugate acid, right? We mixed two solutions together, so we got to find our new volume. So we have moles. So we created 0.012 moles of this solution. But now it is in 90 milliliters. Got to do liters. So 0.012 divided by 0.09. So we have 0.133 molar of this conjugate acid. So we're going to put that here. These are at 0 when we start, and then we're going to minus X. Now this forming an H3O plus is a Ka. We're given Kb. So a couple big things here. One is define the new concentration. Don't forget to do that. The other thing is to convert to Ka. So Ka is equal to Kw over Kb, which is 1 times 10 to the minus 14th over 4.4 times 10 to the minus 4th. Plug that in. 1 EE minus 14 divided by 4.4, PE negative 4. I get 2.27 times 10 to the minus 11th. Now I'm going to solve that, right? Ka is equal to products, one of my x's, two of my x's, and then 0.133 minus x. We're going to use our x's small approximation. And that is equal to 2.27 times 10 to the minus 11th. So I'm going to multiply that number by 0.133. And I get x squared equals 3.02 times 10 to the minus 12th square root. And I get x, which is right here, equal to 1.74 times 10 to the minus 6. Now pH will be negative log of that number. So negative log of that answer, because this is x, right? X is H3O plus, so pH is equal to 5.76. So a lot of work in this, keeping it all straight. Big things are, don't forget concentration, don't forget to switch to Ka. Okay, so 5.76. There we go.